Okay, so let's return to the question that we should be worried about. Why are conformal field theories useful to describe nature? Um, so I'm going to remind you of something that I hope you know about quantum field theories. This is an extremely important idea. This idea is called the renormalization group, and it's something due to Kenneth Wilson. In fact, the renormalization group won a Nobel Prize in physics, and it really gives us the conceptual way that we think about quantum field theory. It's the modern way to think about quantum field theory. So what we think about the Lagrangian density of our theory as being any polynomial in the field and its derivatives. The only thing that we are required to do, the only constraint that we must respect, is that the Lagrangian density, so L, must be Lorentz invariant. You might have other symmetries, and you would impose those symmetries, but that's all you impose. You require that the theory respects the symmetries that you've got. And we start off writing down the Lagrangian. It can be anything we like, as long as it's consistent with Lorentz invariance. Okay, so let's start off. So let's take the Lagrangian density. So what could we write down? Well, first of all, phi to the power of n, that's clearly Lorentz invariant. And we can introduce a different coupling for each of these terms. So we would have a sum over n. I'm not going to include n is equal to 0. That's just a constant. So we'll have a sum from n is equal to 1 to infinity. This is the first term that we could write down. Then if we think about terms linear in derivatives, well, we can't have something that looks like d mu phi. And the reason why we can't have a d mu phi is that that's not Lorentz invariant. It's a 4-vector. So this we cannot have just because we want something that's Lorentz invariant. Now, we could have something like, say, d mu phi, d nu phi. Now, this also is not Lorentz invariant, so we couldn't add that term as it is to the Lagrangian density. But you know that we've got the Minkowski metric eta mu nu. So if we contract d mu phi with eta mu nu, we do get a Lorentz invariant. And well, we usually write this as d mu phi, d mu phi. So this is certainly something that we could add to the Lagrangian density. So let's add here um, d mu phi, d mu phi. That's certainly Lorentz invariant. But if this is Lorentz invariant, I could also multiply it by phi to the m, and that would still be Lorentz invariant. And I could add this for any value of m. So let's add a coefficient here, Cm, and now I will sum over the values of m. And this time I will allow m to be equal to 0. That's still a non-trivial term. It's just the usual kinetic term. So m is equal to 0 to infinity. Now, you might have said that a simpler Lorentz invariant term would have been to add something like d mu phi times by phi to the m, something like that. So why didn't we add that? Well, remember to get the action, so the action is always the integral d4x of the Lagrangian density. So what we're going to do is we'll be taking integral d4x of this term. And then we can always integrate by parts, okay? So now I'm going to integrate by parts. So this is something we did a lot in our last QFT course. So I'll be a little bit quick. If I integrate this by parts, there'll be a minus an integral d4x. We'll have a d mu phi, and then we will have a d mu acting on phi to the m. There is actually another term that I've dropped. This would be a surface term. So remember the surface term? This is a total derivative. So by the four-dimensional version of the divergence theorem or Gauss's theorem, we know that this becomes a term that's evaluated on the surface of space-time, on the boundary of space-time. And at that boundary, all of the fields go to zero. So we always said we'll neglect surface terms, so we don't even bother to write that down. If we evaluate this a little bit, this is minus an integral d4x. We'll have a d mu phi. This derivative will just be m times by the derivative of phi times by phi to the m minus 1. And you can see that this looks exactly like the terms that we've included. So up to integration by parts, we have in fact got everything in our description. Okay, let me just clean a bit of space here. We don't need all of this on our page. Good. Now, what if we tried to include something with three derivatives? Well, if we've got something like d mu phi, d nu phi, d alpha phi, well, we can try to form a Lorentz invariant, and we could contract, say, the mu and the nu index. We can contract any two indices. So we multiply by an eta nu mu, but that still leaves us with one uncontracted index. So we cannot add three derivatives of the field. And in fact, for exactly the same reason, we cannot add five derivatives of the field or seven derivatives. We can never add an odd number of derivatives. A term in the Lagrangian density with an odd number of derivatives, we can only ever have an even number of derivatives. And this is a constraint coming from Lorentz invariant. If we want to write down a term that's Lorentz invariant, we must have an even number of derivatives. So if we look at the terms with four derivatives, say, so let's say we've got a sum here. Let's say we're going to have a sum over p. Let's write this term with four derivatives as follows. Let's say d mu phi, d mu phi. Let's square that. Let's have phi to the power of p. We want some coefficient. Let's call this dp. Again, we'll sum from p is equal to 0 to infinity. You might say, well, let's distribute the derivatives in some other order, and you could do that. And then you could write down terms with 6 derivatives and terms with 8 derivatives, and so on. But I think by now you've gotten the point. So the point is that the Lagrangian that we write down, subject to only the constraint that it's Lorentz invariant, will have an infinite number of terms in it and an infinite number of couplings, okay? So an infinite number of parameters. This is the Lagrangian that we start with. So this would be the Lagrangian density that would describe physics at very high energies. And the code word for saying very high energies, we say this is physics in the ultraviolet. So this would be the UV of the theory. Now, in actual fact, this is not what we're interested in. We're interested in describing physics at our everyday scales. So this UV could be the scale of quantum gravity or something like that, okay? But we're not interested in describing physics at the scale of quantum gravity. We want to describe physics at very much lower energy scales. So what we do is we flow using a renormalization group flow. We flow using the renormalization group to low energies. So this is what we would do. And to flow to low energies, what happens is couplings can change. So there's three kinds of behaviors for our couplings. So let's say three behaviors. So our coupling can flow towards 0. Any coupling that flows towards 0, we call it irrelevant. And at low energies, all of the irrelevant couplings will have disappeared. So some of the couplings that appear here, the GNs, the CMs, the DPs, these may be irrelevant. They would flow to 0. We've also